60 meters beneath the surface of one of North America's most famous lakes, there are trees. Not driftwood, not broken branches tumbled in by storms. Stumps, rooted trunks. Trees that once stood in open air, caught sunlight, and grew rings for decades, possibly centuries, on ground that is now buried under a volume of water large enough to cover the entire state of California to a depth of 14 inches. And when researchers pulled samples from that submerged wood and sent them for radiocarbon dating, the results came back between 4,800 and 6,300 years old. Parts of Lake Tahoe that today sit under 60 feet of cold Sierra Nevada water were once dry land, dry enough and dry long enough for forests to take root and grow. That alone would be enough to make Tahoe one of the strangest lakes on the continent, but it is only the beginning. Because beneath Tahoe's surface, scientists have also found the geological scar of a catastrophic landslide so massive it generated a tsunami inside the lake. They have found a steamship that was supposed to sink to 30 meters and instead slid down an underwater cliff to 140. They have found stone tools carved by human hands now sitting below the waterline. They have found hot springs pushing geothermally heated water directly into the lake from below. And they have found animals, living animals, that had never been described by science until the 21st century. 6 discoveries, all from the bottom of a single lake, and every one of them changes something about what we thought we understood. This is what Lake Tahoe has been hiding. Let us start with the forest. Lake Tahoe sits at an elevation of roughly 6,225 feet in the Sierra Nevada, straddling the border between California and Nevada. It is the largest alpine lake in North America by volume, holding approximately 39 trillion gallons of water. Its maximum depth reaches more than 1,600 feet, making it the second deepest lake in the United States after Crater Lake in Oregon. The water is famously clear. On a calm day, you can see objects more than 70 feet below the surface. But clarity is not the same thing as transparency about history. Tahoe looks placid, postcard blue, timeless, and that is exactly the problem. Because the lake has not always looked the way it does now. It has not always been this deep. It has not always reached this far up its shoreline. And the proof is sitting on the bottom. In the shallower margins of the lake, researchers working with underwater surveys and sediment cores began documenting something that did not fit the assumption that Tahoe had always existed at roughly its present level. They found wood, not small fragments washed in by rivers or avalanches, but substantial tree remains, stumps, and trunks, some of them in positions suggesting they had not traveled far from where they originally grew. Several specimens were found at depths exceeding 20 meters below the modern surface. Now, here is the critical detail. Trees do not grow underwater. They do not germinate on a lake bed. For a forest to establish itself at a location that is now 20 meters beneath the surface of Lake Tahoe, the water level of the lake had to have been dramatically lower than it is today. Not just a few feet lower during a dry summer, tens of meters lower, low enough to expose what is now submerged lake bed as dry, habitable ground. And it had to stay that low for a long time, long enough for trees to sprout, grow, and reach substantial size. When researchers extracted samples from this submerged wood and subjected them to radiocarbon dating, the ages clustered in a range between roughly 4,800 and 6,300 years before present. That places the period when these trees were alive squarely within the mid-Holocene, a stretch of Earth's climatic history that paleoclimatologists have long recognized as significant. Multiple lines of evidence from across western North America, pollen records, lake sediment cores, tree ring chronologies, and geomorphological data point to prolonged episodes of severe drought during this period. Not a single dry year, not a decade, centuries-long megadroughts that would dwarf anything recorded in the modern era. What the submerged trees tell us is that Lake Tahoe did not escape these droughts. The lake dropped. It dropped far, and it stayed low long enough for ecosystems to colonize the newly exposed land. Scientists reconstruct these ancient water level changes using several converging methods. The tree remains themselves provide direct evidence. Their depth below the modern surface sets a minimum for how far the lake fell, and their radiocarbon ages establish when that drop occurred. Sediment cores extracted from the lake bed can reveal changes in the types of material being deposited. shifts from deep water sediments to shallower deposits, or even evidence of subaerial exposure, where the lake bed dried out entirely in certain areas. Researchers also study ancient shoreline features, wave-cut terraces, old beach ridges, and erosional notches carved into rock at elevations that no longer correspond to the modern waterline. Each of these lines of evidence acts as a kind of geological bookmark, recording a moment when the lake surface sat at a particular height. Taken together, the picture that emerges is not one of a single catastrophic event. It is something more sobering. Lake Tahoe experienced prolonged periods, possibly lasting several hundred years, during which it received far less water from precipitation and snowmelt than it lost to evaporation and outflow. The lake shrank. Its surface dropped by what researchers estimate could have been tens of meters. The floor of the basin that we now see covered by deep blue water was, for generations, open ground. And then, the climate shifted again. Precipitation increased. Snowpack rebuilt. The lake rose. The forests that had colonized the exposed margins were drowned, their trunks and stumps entombed in cold, oxygen-poor water that slowed decomposition to an extraordinary degree. Thousands of years later, they are still there. What makes this discovery more than a geological curiosity is what it implies about the future. The droughts that dropped Tahoe's level during the mid-Holocene were driven by natural climatic variability, long-term shifts in atmospheric circulation, ocean temperatures, and solar forcing. They happened without any contribution from industrial greenhouse gas emissions. The modern climate of the Sierra Nevada is changing again, this time under the influence of anthropogenic warming. If Tahoe dropped by tens of meters in response to past droughts, the question becomes unavoidable. How resilient is the lake's current water level to future climatic stress? There is also a subtler question. The submerged forests that have been documented so far were found in relatively shallow areas accessible to divers and survey equipment. Lake Tahoe's deepest point exceeds 500 meters. Its underwater topography includes steep slopes, submerged ridges, and vast expanses of lakebed that have never been systematically surveyed at high resolution. If trees grew at the margins during severe droughts, could there be additional evidence of even lower water levels preserved in deeper, less accessible parts of the basin? Could ancient shoreline features exist at depths that no one has yet examined closely? The answer is that we do not know, because the deep floor of Tahoe remains one of the least explored landscapes in North America. The trees are still down there, rooted in sediment that was once dry soil, standing in water that was once open air, silent witnesses to a version of Lake Tahoe that no living human has ever seen. And the trees are not the most violent thing the lake is hiding. In the late 20th century, researchers began using multi-beam sonar and other bathymetric technologies to create detailed maps of Lake Tahoe's underwater terrain. Multi-beam sonar works by emitting fans of acoustic pulses toward the lakebed and measuring the time each pulse takes to return. By collecting millions of individual depth measurements, scientists can construct three-dimensional models of the bottom with remarkable precision, revealing features that are invisible from the surface. When they turned this technology on the area around McKinney Bay, on the western shore of Tahoe, what they found was not subtle. A massive section of the mountainside had collapsed into the lake. The volume of displaced material was staggering. Researchers estimated it at several cubic kilometers. To put that in terms that mean something, imagine a block of rock and earth roughly a mile long, a mile wide, and several hundred feet thick breaking away from the slope and plunging into the water. The debris spread across the lake floor in a fan of jumbled rock, sediment, and shattered terrain that was clearly visible in the sonar data. This was not erosion. This was not gradual slumping. The bathymetric signature was consistent with a catastrophic slope failure, a sudden, massive landslide that dumped an enormous volume of material into Lake Tahoe in what may have been a single event, or at most a very short sequence of failures. And here is where the physics becomes terrifying. Lake Tahoe is an enclosed basin. It has no ocean to absorb the energy of a displacement event. When a landslide of this magnitude enters a confined body of water, the energy has nowhere to go except into the water itself. The displaced volume generates a wave, and in an enclosed lake, that wave does not dissipate across thousands of miles of open ocean. It crosses the basin, reflects off the opposite shore, and bounces back. Depending on the geometry of the collapse and the shape of the basin, The initial wave and its reflections can produce water movements of extraordinary height and destructive power. Researchers who modeled the McKinney Bay event concluded that it would have generated a tsunami within Lake Tahoe. The estimated wave heights varied depending on the model parameters, but some scenarios produced waves that would have been tens of meters high at certain points along the shoreline. A wall of water taller than a 5-story building racing across the surface of an alpine lake. But here is what separates this from speculation. The evidence is not limited to the landslide debris itself. When researchers examined the lakebed in detail, they found additional features that appeared to be directly connected to the event. Among the most striking were boulder ridges, elongated mounds of coarse material, roughly 1 to 2 meters high, extending for distances of up to approximately 2 kilometers across the lake floor. These ridges did not resemble typical sediment deposits formed by slow accumulation. Their morphology was consistent with material transported and deposited by powerful, high-energy flows, the kind of flows that would be generated when a massive volume of water is suddenly displaced, surges across the basin, and then interacts with the bottom sediments. Later investigations identified something else, a network of underwater channels carved into the terrain around the lake's margins. These channels appeared to record the path of water that had been pushed onto land by the tsunami and then drained back into the basin. When a large wave inundates a shoreline, the returning water does not flow back gently. It carves, it erodes, it cuts channels as it rushes downslope, carrying sediment and debris. The channels visible in the bathymetric data around Tahoe are consistent with exactly this process. So the reconstruction, pieced together from the physical evidence on the bottom, looks something like this. A large section of the western slope failed catastrophically. The debris plunged into the lake, displacing an enormous volume of water almost instantaneously. A wave, or series of waves, radiated outward from the collapse zone. These waves struck the surrounding shoreline, inundating low-lying areas. The water then retreated, carving return flow channels as it drained back into the basin. The boulder ridges on the lakebed record the powerful currents generated during this entire process. What we do not know with precision is exactly when this happened. Dating a subaqueous landslide is far more difficult than dating a piece of wood. Estimates have placed the McKinney Bay event at roughly tens of thousands of years ago, but the exact age remains uncertain. We also do not know the precise height of the waves with certainty, because wave modeling depends on assumptions about the volume of material, the speed of the collapse, the geometry of entry into the water, and the bathymetry of the lake at the time of the event, all of which carry margins of error. But the core finding is not in doubt. The physical evidence of an enormous mass movement is clearly preserved on the bottom of Lake Tahoe. The landslide happened, it was massive, and the laws of physics guarantee that it displaced a catastrophic volume of water. What do you think would happen if an event like this occurred today, with communities, roads, and infrastructure lining the entire shore of the lake? How much warning would there be? Write your answer in the comments because this is not an abstract question. Geologists have identified other potentially unstable slopes around Tahoe's basin. The McKinney Bay slide was not necessarily a one-time anomaly. The lakebed also preserves evidence of events that are not ancient at all. Some are well within the reach of written records, and at least one involves a plan that went spectacularly wrong. In the late 19th century, Lake Tahoe was not the recreational paradise that modern visitors experience. It was a transportation corridor. The communities scattered around the lake's 60-odd miles of shoreline were connected less by roads, which were rough, seasonal, and in many cases barely passable, than by water. Steamships carried passengers, mail, freight, and supplies from one lakeside settlement to another, and the largest, most elegant of these vessels was the SS Tahoe. Built in San Francisco in 1895 and 1896, the SS Tahoe was a steel-hulled passenger steamer approximately 169 feet long, roughly 52 meters. She was assembled in sections, transported over the Sierra Nevada by rail, and riveted together at a lakeside shipyard. When she entered service, she was the finest vessel on the lake, a floating hotel with a dining room, a social hall, and accommodations for passengers who expected comfort. For decades, she connected communities around Tahoe, carrying everything from tourists to timber. But by the 1930s, roads had improved. Automobiles had arrived. The era of the steamship on Lake Tahoe was ending. The SS Tahoe was withdrawn from regular service. and the question became what to do with a steel ship that was too large to move overland and too expensive to maintain. The answer, eventually, was to sink her. In 1940, the decision was made to scuttle the SS Tahoe in Glenbrook Bay, on the Nevada side of the lake. The plan, as it has been described in historical accounts, was not simply to dispose of the vessel. The intention was reportedly to sink her at a controlled depth, roughly 30 meters, or about 100 feet, where she would rest on the bottom and serve as an underwater attraction. Tourists in glass-bottom boats would be able to peer down through Tahoe's famously clear water and see the intact ship sitting on the lakebed. It was an early, ambitious version of what we would now call an artificial reef or underwater heritage site. It did not work. The SS Tahoe was towed out, her seacocks were opened, and she began to take on water. She sank. But the lakebed beneath Glenbrook Bay is not a flat plain. Like much of Tahoe's underwater terrain, it drops away steeply. The lake occupies a graben, a block of Earth's crust that subsided between parallel faults, and its sides plunge at angles that in many places resemble the walls of a canyon more than the gentle slopes of a typical lakebed. When the SS Tahoe settled, she did not stop at 30 meters. She began to slide. The hull, now free of buoyancy and pulled by gravity, moved down the submerged slope. She kept going. By the time she finally came to rest, the bow was sitting at approximately 117 meters, roughly 385 feet. The stern had reached approximately 140 meters, around 460 feet. She had overshot the planned depth by more than 100 meters. The glass-bottom boats would see nothing. For years afterward, the exact condition and location of the wreck were poorly understood. It was known that the ship had sunk too deep, but detailed information was limited by the extreme difficulty of reaching those depths. Lake Tahoe is a high-altitude environment. Its surface is over 6,000 feet above sea level. Diving at altitude introduces physiological complications that make deep dives significantly more dangerous than equivalent depths at sea level. The reduced atmospheric pressure at Tahoe's elevation means that decompression calculations must be adjusted, and the risks of decompression sickness increase. Add to that the near-freezing water temperatures at depth, and you have an environment that is hostile even to experienced technical divers. It was not until advances in remotely operated vehicles and deep diving technology that researchers were able to locate and systematically document the wreck. What they found was remarkable. The cold, fresh water of Lake Tahoe had preserved the SS Tahoe to a degree that salt water would never have allowed. The hull was largely intact. Structural features were recognizable. The ship sat on the slope at an angle, her bow higher than her stern, as if she were still in the process of sliding down the underwater mountainside. Details that would have corroded or been consumed by marine organisms in the ocean were still visible, a testament to the preservative qualities of Tahoe's cold, low-nutrient water. The wreck was eventually recognized as a historically significant artifact. She represents one of the last surviving examples of the large passenger steamships that once formed the primary transportation network on Lake Tahoe. In recognition of that significance, the SS Tahoe was listed on the National Register of Historic Places, an unusual distinction for a vessel lying more than 100 meters below the surface of a freshwater lake. There is something almost cinematic about her story. A ship built in pieces, hauled over a mountain range, assembled on the shore of an alpine lake, and put into service connecting communities that had no other reliable way to reach each other. She operated for decades. Then the world changed. Cars replaced steamships, and when the time came to retire her, even the plan to give her a dignified second life as an underwater monument failed. She slid past the depth anyone intended, down a slope that no one had adequately considered, and came to rest in cold darkness far beyond the reach of glass-bottom boats. If this is the kind of story that hooks you, real history sitting at impossible depths waiting to be found, subscribe to the channel, because Lake Tahoe is far from the only body of water on this planet hiding things that rewrite what we thought we knew. And the deeper we look, the stranger it gets. The next discovery does not come from the deep water. It comes from the edges, and it was made not by sonar or submersibles, but by the lake itself during a drought. Around Lake Tahoe, archaeologists have long documented evidence of sustained indigenous habitation stretching back thousands of years. The Washoe people, whose ancestral territory includes the Tahoe Basin, maintained a deep and enduring relationship with the lake and its surrounding landscapes. Archaeological sites around the shoreline include habitation areas, tool scatters, and a category of artifact that is both unmistakable and immovable: bedrock mortars. A bedrock mortar is exactly what it sounds like. It is a depression, a cup-shaped hole that has been deliberately ground into the surface of an exposed rock outcrop. These features are not natural. Water erosion can create smooth depressions in stone, but bedrock mortars have a distinctive morphology. They tend to be circular or slightly oval, with relatively uniform walls and a rounded base, shaped by the repeated impact and grinding motion of a handheld stone pestle. Over years, decades, or even centuries of use, the pestle wears a progressively deeper and more defined cavity into the bedrock. The result is a permanent record of sustained food processing activity. Indigenous communities throughout California and the Great Basin used bedrock mortars to process a wide range of plant foods. Acorns were among the most important, but seeds, roots, dried berries, and other materials were also processed. A single outcrop might contain dozens of individual mortar cups, representing a communal work area used by many people over long periods. These sites are not incidental. They are anchored to specific locations chosen for their proximity to food sources, water, shelter, and the social geography of the community. And here is where Lake Tahoe introduces a complication. Some of these bedrock mortar features have been documented at elevations that place them below the modern waterline of the lake, or within the zone of fluctuation where the lake periodically covers and uncovers the rock. During the severe droughts of the 1920s and 1930s, Lake Tahoe's water level dropped significantly. As the shoreline retreated, it exposed rock surfaces near the lake's outlet that had been submerged or periodically inundated under normal conditions. On those newly exposed surfaces, researchers found bedrock mortars, grinding features carved by human hands now positioned where the lake routinely covers them. Additional shallow submerged mortar features have been reported at other locations around the lake, though systematic underwater archaeological surveys of Tahoe's full shoreline remain incomplete. The implications are straightforward but important. People use these rocks to grind food. That activity requires dry, stable, accessible rock surfaces. You do not process acorns while standing in knee-deep water. If the mortars are now at or below the waterline, then at the time they were being used, the lake surface must have been lower than it is today, or at least lower than the elevation of those specific rocks. This is a different kind of evidence than the submerged forest. The trees tell us about conditions thousands of years ago, during the mid-Holocene megadroughts. The bedrock mortars tell us about conditions during the period of human use, which could overlap with the same era, but could also represent entirely different, more recent episodes of lower water. The Washoe and their ancestors have occupied the Tahoe Basin for thousands of years, and lake levels have fluctuated repeatedly throughout that time. A mortar exposed during a 20th century drought might have been carved and used during a medieval dry period, during a mid-Holocene low stand, or during some other interval entirely. Without direct dating of the mortar use, which is extremely difficult since grinding stone does not lend itself to radiocarbon analysis the way wood does, we cannot simply assume that the submerged mortars and the submerged trees date to the same episode. What we can say is that both types of evidence point to the same broader reality. Lake Tahoe's water level has not been constant. It has moved, sometimes dramatically, and the people who lived along its shores experienced those changes directly. They worked on rocks that the lake later reclaimed. They built their routines around a shoreline that was not where we see it today. There is a quiet power in that image, a woman kneeling on a flat stone near the water's edge, grinding acorns with a smooth river cobble, working a depression that her mother and her grandmother had used before her. The lake lapping a few feet away but not touching the stone, generations passing. And then the water rising, inch by inch, season by season, until the stone disappears. The mortar cups fill with silt. The surface that once rang with the sound of grinding is covered by cold, still water. And it stays there, waiting, until a drought in the 20th century pulls the lake back down and reveals what everyone had forgotten was there. Now before we leave the margins and head back toward deeper water, there is one more discovery along Tahoe's shoreline that most visitors have never heard of, and it involves something coming up from below, not sinking down. On the northern shore of Lake Tahoe, near the community of Brockway, there is a geothermal feature that seems almost paradoxical. Lake Tahoe is cold. Its average surface temperature hovers around 50 degrees Fahrenheit in summer and drops into the low 40s in winter. At depth, the water is even colder. Near the bottom, temperatures approach 39 degrees Fahrenheit year-round. This is an alpine lake fed by snowmelt, sitting at over 6,000 feet of elevation. The word that comes to mind is frigid. And yet, along the northern shore, hot water has been documented emerging directly into the lake. The feature known as Brockway Hot Spring was investigated historically, and researchers documented multiple vents where heated groundwater discharged at the surface. At one vent, the recorded water temperature was approximately 137 degrees Fahrenheit, 58 degrees Celsius. That is hot enough to cause a serious burn, hot enough to brew tea, and it was coming out of the ground at the edge of an alpine lake surrounded by pine forests and granite peaks. How is this possible? The answer lies beneath the surface, not beneath the lake, but beneath the landscape itself. The Sierra Nevada and the adjacent Basin and Range Province are geologically active regions. The Earth's crust in this area is being stretched and pulled apart by tectonic forces, a process that creates faults, fractures in the rock that can extend deep into the crust. Lake Tahoe itself exists because of this faulting. The basin that holds the lake is a graben, a block of crust that dropped between parallel faults as the surrounding terrain was pulled apart. These same faults that created the basin also create pathways for water. Precipitation and snowmelt seep into the ground, percolating downward through permeable rock and along fracture zones. As water descends, it encounters increasing temperatures. The Earth's interior grows warmer with depth, a phenomenon known as the geothermal gradient. In most places, the temperature increases by about 25 to 30 degrees Celsius per kilometer of depth. Water that circulates deep enough absorbs that heat. If the fracture network provides a pathway back to the surface, the heated water can rise, driven by its lower density compared to the cooler water around it, and emerge as a hot spring. At Brockway, the geometry of the faults apparently provides exactly this kind of plumbing system. Cold water enters the ground at higher elevations, descends along fractures, is heated by the natural warmth of the Earth's interior, and rises back toward the surface along a different set of fractures. When it reaches the edge of the lake, it discharges into Tahoe, warm, mineral-laden water entering a body of near-freezing snowmelt. The Brockway area was once home to a resort that capitalized on the hot mineral water. Visitors came to bathe in the naturally heated springs, a practice common throughout the American West wherever geothermal features were accessible. But changes in the shoreline, including fluctuations in Tahoe's water level and modifications to the landscape, left portions of the historical spring area submerged or altered. The original resort era has passed, but the geothermal phenomenon has not. Modern documentation from the Tahoe Regional Planning Agency continues to recognize warm, mineralized groundwater discharging into Lake Tahoe in the Brockway area. The springs have not disappeared. They have simply become less visible, partly because some discharge points are now at or below the waterline, and partly because the development patterns around the lake have changed. Scientists find these springs interesting for several reasons. The chemistry of the water carries information about the rocks it has passed through and the temperatures it has reached. By analyzing the dissolved minerals, silica, sodium, chloride, sulfate, and others, researchers can estimate how deep the water circulated and how long it spent underground. Temperature measurements at the discharge point, combined with chemical data, help constrain models of the subsurface plumbing system. In a region where understanding groundwater flow is critical for managing both water quality and geothermal resources, every natural discharge point is a window into processes that are otherwise invisible. But there is an important distinction that needs to be made clearly, because this is where popular imagination tends to run ahead of the science. The existence of hot springs near Lake Tahoe does not mean there is a magma chamber beneath the lake. It does not mean Tahoe is sitting on top of a volcano that could erupt. The Tahoe Basin is not Yellowstone. The heat source for the Brockway Springs is not molten rock near the surface. It is simply the normal geothermal gradient, the background heat of the Earth's interior, accessed by water that circulates deep enough along fault-controlled pathways. That said, the phenomenon is genuinely remarkable on its own terms, without any need for volcanic drama. groundwater is being heated miles beneath the surface, traveling through fractures in the Earth's crust and discharging directly into one of the coldest, clearest alpine lakes in North America. At the spot where the hot water meets the lake, two completely different thermal regimes collide. One driven by snowmelt and mountain weather, the other driven by the deep interior of the planet. If you know someone who would find this kind of story fascinating, real science, real mysteries, no exaggeration needed, send them this video, because we have one more discovery to go, and it might be the most surprising of all. Not because it is the largest, because it is the smallest. When most people think about discovering a new species, they imagine an expedition into a remote jungle, a team of biologists hacking through undergrowth, and eventually, a dramatic encounter with some previously unknown bird, mammal, or reptile. The animal is large enough to see, charismatic enough to photograph, obviously, unmistakably new. The reality of species discovery in the 21st century is usually nothing like that. In Lake Tahoe, two species new to science were discovered, not in a dramatic underwater encounter, but under a microscope, in a laboratory, by researchers examining the tiny organisms that live in and on the lake's bottom sediments. The animals in question are harpacticoid copepods. If that term means nothing to you, you are not alone. Harpacticoid copepods are microscopic crustaceans, relatives of crabs and shrimp, but so small that most are measured in fractions of a millimeter. They live in the spaces between sediment grains, in the thin film of water coating submerged surfaces, and in the organic debris that accumulates on the floors of lakes, rivers, and oceans. They are everywhere in aquatic environments, and almost no one outside of specialist taxonomy has ever heard of them. But here's the thing about copepods. Despite their size, they are extraordinarily diverse. Thousands of species have been described worldwide, and thousands more are believed to exist undescribed. Each species is defined by a specific combination of anatomical features: the number and shape of body segments, the structure of the swimming legs, the form of the antenna, the arrangement of tiny hair-like projections called setae, the shape of the reproductive structures, and dozens of other minute characteristics. To identify a copepod to species, a taxonomist must dissect the animal under high magnification, mount the body parts on slides, and compare each structure against the published descriptions of every known species in the relevant group. It is painstaking, exacting work, and it is the only way to determine whether an organism is a known species or something new. When researchers collected sediment samples from Lake Tahoe and examined the harpacticoid copepods living within them, they found specimens that did not match any previously described species. The leg segments were wrong. The setae were in different positions. The proportions of the body did not correspond to any known member of the genus. After careful comparison with all described species in the relevant taxonomic group, the researchers concluded that they were looking at not one, but two species that had never been formally recognized by science. In 2015, the two species were formally described and named: Athayella tahoensis, named for Lake Tahoe itself, and Athayella tessiae, named in honor of an individual connected to the research. With those publications, two animals that had been living in Lake Tahoe for an unknown length of time officially entered the scientific record for the first time. Now, why does this matter? Two microscopic crustaceans, invisible to the naked eye, living in bottom mud. Who cares? The answer has to do with a concept called endemism. Researchers have suggested that these species may be endemic to Lake Tahoe, meaning they are found naturally in this one lake and nowhere else on Earth. If that is confirmed, it has significant implications for how we understand the lake as an ecosystem. Lake Tahoe is old. Not old in the way that a building or a city is old in geological terms. The basin began forming roughly 2 to 3 million years ago, as faulting and volcanic activity shaped the landscape of the northern Sierra Nevada. The lake that fills the basin has existed, in some form, for a very long time. That duration matters because time is one of the essential ingredients for the evolution of unique species. When a population of organisms becomes isolated in a specific habitat, a remote island, a deep cave, an enclosed lake, and that isolation persists for thousands or millions of years, the population can diverge from its relatives elsewhere. Mutations accumulate. Natural selection favors adaptations to the local environment. Over enough time, the isolated population becomes distinct enough that taxonomists recognize it as a separate species. This is the basic engine of endemic speciation, and it has produced some of the most remarkable biodiversity on the planet, from the finches of the Galapagos to the cichlid fishes of the African Great Lakes. Lake Tahoe, with its great depth, its long geological history, and its relative isolation as a high-altitude basin, provides exactly the kind of stable, enclosed environment where endemic species can evolve and persist. The discovery of Athayella tahoensis and Athayella tessii suggests that this process has been operating in Tahoe's deepest sediments, producing unique lineages that have gone unnoticed simply because almost no one was looking. And that raises a question that should make any biologist pause. How many other undescribed species are living in Lake Tahoe right now? The honest answer is that we do not know. The deep sediments of the lake, the environments below 100 meters, 200 meters, 500 meters, have been sampled, but they have not been comprehensively surveyed for microscopic fauna. Every sediment grab, every core sample, examines a tiny fraction of the total habitat. The organisms living in those sediments are small, difficult to collect, and time-consuming to identify. It is entirely plausible that additional undescribed species exist in Tahoe's deep habitats, waiting for a taxonomist to examine them. After more than a century of scientific attention focused on one of the most famous, most visited, most photographed lakes in North America, a lake whose water clarity is monitored annually, whose fish populations are managed, whose shoreline has been developed and studied and regulated, researchers could still reach into the bottom mud and pull out animals that science had never formally named. That fact alone tells you something about how little we actually know about what lives beneath the surface of even our most familiar waters. And that, in the end, is the thread that connects all 6 of these discoveries. The submerged forest tells us that the lake we see today is not the lake that existed 6,000 years ago. The geological scar of the McKinney Bay landslide tells us that the calm surface hides evidence of a catastrophe powerful enough to generate a tsunami in an alpine basin. The SS Tahoe tells us that even deliberate, planned human interaction with the lake can go spectacularly wrong when people underestimate the terrain beneath the water. The bedrock mortars tell us that human communities built their lives around a shoreline that has since moved, and that the lake has reclaimed the very rocks where people once ground their food. The hot springs tell us that the Earth's deep interior is actively connected to the lake through fractures in the crust, pushing heated water into a body of frigid snowmelt. And the copepods tell us that unique life has been evolving in Tahoe's sediments, unrecognized, for longer than we can easily estimate. 6 completely different discoveries, 6 different scientific disciplines, 6 different timescales, from millions of years of evolutionary isolation to thousands of years of drought, to the decades of a steamship's career, to the minutes it took for a mountainside to collapse into the water. And all of them from the bottom of a single lake. Lake Tahoe is 22 miles long and 12 miles wide. Its surface shimmers blue in every postcard, every photograph, every drone shot uploaded to social media. Millions of people visit every year. They swim, they kayak, they take pictures of the sunset, and almost none of them have any idea what is sitting directly beneath them. A drowned forest, a tsunami's fingerprint, a steamship on a cliff, grinding stones reclaimed by the water, hot springs from deep in the earth, and animals that had no name until 12 years ago. The next time someone shows you a picture of Lake Tahoe and tells you it is beautiful, agree with them. It is. But beauty is the easy part. The difficult part, the part that keeps researchers coming back with sonar and submersibles and microscopes and sediment cores, is everything the beauty is hiding. And the most unsettling possibility of all? After 6 discoveries, we have almost certainly not found everything. The deepest parts of Lake Tahoe remain among the least explored places in North America. Whatever else is down there, it is still waiting.